Hey. The idea of this video is I think we just need to do more examples of this concept of proportionality. So there will be, depending on when you watch this, there will be a course slide that is available on in lecture 29 that will kind of go through this as a course slide, but I think really this kind of comes best learned through examples. So the idea here is that, again, I rarely want us to actually plug in numbers. Sometimes on the homework, right? You have more time, you can be more careful, you can use a calculator. But that's not always going to lead to the insight that I think you can get from an equation when you just are plugging numbers in blindly and get some number with 6 decimal spots and who cares, let's just move on. Usually what I want to do, professionally, I do this all the time, is that when I have some sort of equation, I usually try to do some sort of comparisons. Just like if I have two objects and they have some gravitational force between them and then I move them twice as far away, does the gravitational force get weaker, stronger, stays the same? And then maybe I can say, does it get twice as, is it 1/2 as strong, or is it twice as strong, or is it 10 times as strong? And the cool thing is that you can do this without having to actually plug in messy numbers. You just have to focus on factors. Right? When I say something changes by a factor of 2, that factor of 2 is what we focus on and can actually learn something from these equations. So I thought I would do 6-ish examples of this, of a way of doing this that is not perhaps the formal way that we would have physics majors do it, but gets you the right answer, and I think kind of makes it a little simpler in terms of how you might do this. And I think then you'll see that this sort of approach can be very helpful when we're thinking about things. So let's take this example. This was, I think, on one of the quizzes. Planet Eric orbits star Carla in a circular orbit with a semi-major axis of 3 AU. If the orbit changed to have a semi-major axis of 6 AU instead, the gravitational force between Carla and Eric is 4 times bigger, 2 times bigger, stays the same, is half as large, or is 1/4 as large. So the idea here is that if you think about, we're always comparing two things. There's something that we are comparing. Here we are comparing the gravitational force when they are located at some location, and then we're going to compare that to the gravitational force when they are twice as far away. So there is a factor of 2 there. What changed in this case? The distance changed by a factor of 2. It went from 3 to 6. That factor is what's important. So in these sorts of ratio proportionality problems, you want to identify the factors that something is changing. So I think I would say that the way to do this is through a couple steps. I'll just follow what's on the course slide that you might have available with some elaboration. The first thing to do is to identify the relevant formula. So in this case, you have to look, and it seems like that we're talking about gravitational forces, and it seems like that's what we're trying to figure out. How does the gravitational force change? So ideally, I want some equation that says gravitational force equals blah. And then what goes on the right-hand side will have variables as well. And some of those variables might be changing. Like in this case, the distance changes. Well, some of those variables might not change at all. For example, we'll see the masses of planet Eric and star Carla don't change. So again, before I get ahead of myself, step 1, I would say, is to identify the relevant equation. Now, in this case, we are talking about the gravitational force. So the relevant equation in this case is that the gravitational force F is equal to some constant g m1 times m2 divided by d squared. Again, you have all equations you would ever need on a cover sheet, but you need to know which is which and what the symbols represent. So again, this is, so here in this case, right, this is just a constant. You can look it up in a book. These are the masses of the two objects. Faculty are having too much fun in the office next to me. And then this d is the distance between the masses. And then F is, of course, the gravitational force. Let's try grav force. Right, that's the first step. Right, identify the relevant equation. And in this case, we are asking, if we go back up to the prompt, it is asking about what? It is asking how the gravitational force is changing, right? Is it 4, 2, 1, 1/2, 1/4? You know, how is the gravitational force changing? So in this case, you then want to solve for, if you need to, you can solve for the relevant variable. In this case, we don't have to do anything. It's already solved for us. It already is in the form of F equals. Right, we want to see how the force is changing, so I want to be able to write that as a bunch of other variables and constants. Now the next step is, you know, notice that for some of these things, we don't have numbers for them. G is a constant. You can look it up in a book. We do have a number for that, technically. D, we did have some numbers for. You know, D started at 3 and becomes 6. But then notice we don't have anything for the masses. So then we can assume that the masses are staying the same. Else I would say, you know, Carla became twice as massive or Eric became 10 times as massive, whatever. In this case then, the next step is to, for all the variables on the right-hand side, so for all variables on the right-hand side, identify the factor by which it changes, if at all. Identify the factor. And by that, I'm emphasizing it's not the actual value of the variables I care about, but it's the factor by which it changes, if at all. Let's see, the factor by which the variable changes. Again, if at all. Sometimes it won't change. That only means it changes. You know, you could think of it, if it doesn't change, then you could think of it that it changes by a factor of 1. You know, it goes from 10 kilograms to 10 kilograms. That's a fact. You know, those are related by multiplying by 1. It's a factor of 1. So I'm going to write down all of these factors. You can also remove constants in this case. They will not come into the analysis. By remove constants, you know, we are just going to, right, you could just plug in 1 for all the constants, or just take them away. So the step here is then, right, G is going to go away, so I'm going to set G to 1, because it's a constant. And then I'm going to ask, by what factor does the mass 1 change? By what factor does the mass 2 change? And by what factor does D change? So the masses are not changing, so I'm going to write 1 for both of those. In this case, they don't change. But then D went from 3 AU to 6 AU. But again, remember, we're focusing on the factor. So that changes by a factor of 2. 3 goes to 6. That's a factor of 2 bigger. If it was 6 going to 3, it'd be a factor of 1/2. But since 3 is going to 6, that is a factor of 2. Again, emphasizing that this is a factor of 2 increase. Right, it starts at 3, it goes to 6. Notice 3 and 6 have not appeared anywhere yet. What I've identified here, and what's going to be relevant, is the factors for all the variables. And you do that for every variable that's on the right-hand side. So there's a G, an M1, an M2, and a D. And I've identified for each of them the factor. Right? Constants are just 1. The masses don't change, and then distance doubles. And then what's kind of cool about this trick is that if you then want to find the factor by which the gravitational force changes, you just plug in all of these factors. So plug in factors into the equation to get not the value of the gravitational force, but to get the factor the gravitational force changes. So in this case, F is G M1 M2 over D squared. I'm now going to plug in the factors. So G1 M1 1 M2 1 divided by D squared, or 2, can't forget that square. The exponents are key, can't forget the exponents. So then this looks like it's 1 times 1 times 1, and then 2 squared is 4. So the answer is 1/4. So what does this say? That the gravitational force is 1/4 as large. Or another way of saying that is that it decreases by a factor of 4. Right, it's 1/4 as big. So in this case, then, the answer would be E in this case. And again, you might have been able to qualitatively reason this out, knowing that since distance is in the denominator for this equation, that if D gets bigger, the entire thing must go down. We did that already, right? That's qualitative reasoning. Now we're trying to be a little bit more quantitative. But again, not focusing on me plugging in exact numbers, right? Looking up how many meters are in an AU and looking up G, and no. If I know how things are changing, what factors they change by, then I can use those factors to, in this case, determine that the gravitational force decreases by a factor of 4, or is 1/4 as large. And again, notice that the 3 and the 6 never appeared anywhere, right? We never used the exact values. We only cared about the factor that they were different by. This was the alternative version on the quiz. Planet Eric orbits star Carla in a circular orbit. If the mass of Eric triples with everything else staying the same, the gravitational force between Carla and Eric does what? So I would say, again, identify the relevant equation. I want to figure out the gravitational force and by what factor it changes by. And so I know then that the formula is G M1 M2 over D squared for the two masses. In this case, right, it seems like it's going to be Carla, and it's going to be Eric. They're separated by some distance D. So maybe we'll call Carla M1 and Eric M2. So if the mass of Eric triples with everything else staying the same, the gravitation, So then, step 1, right, what's the relevant equation? Step 2, do we need to isolate the variable we're interested in? And you're interested about the gravitational force, it already is written as F equals something. So then I would say, this is step 1 and 2 in a sense, because we didn't have to really do anything with 2. Step 3 is to write down the factors by which every variable changes. So again, it looks like there are 4 I have to think about. I have a G, I have an M1, an M2, and a D. So in this case, and you could just get rid of the constants. Right? Anything that's a constant, like the G, I could just make it go. I could just remove it. Similarly, like if there's 4s or pi's, you could just remove them or set them or turn them into 1. Right, so I might say, removing constants, I might do it this way too. Removing constants, then F equals M1, M2 over D squared. Now again, remember, we're not actually calculating the exact value of the force. Else, this is nonsense. I can't just get rid of G. But since we're dealing with multiplicative factors, it turns out, if you did this kind of the, I don't want to say professional way, but the kind of way we would teach, the physics majors, they would be taking ratios of equations, and then the G's would all be canceling out. So essentially, that's what I'm doing by just setting the constants equal to 1. So then in this case, then the factors for each of these is M1, which we said was Carla, is not changing. M2, which was Eric, is tripling. And the distance between them, we said, is not changing because everything else is staying the same. And then 4, plug in the factors. So then the factor by which F changes looks like it's M1, which is 1, M2, which is 3, and then divided by D squared, which is 1 squared. 1 squared is 1, so it looks like this is just 3. So in this case, then, the gravitational force is 3 times larger. In that case, one of the masses goes up, therefore the gravitational tug between the two increases as a result. So you could imagine I could do something like, I could say like the mass of Eric triples and their distance doubles. Then you could have 2 variables that are changing. That's fine. Then you just are plugging in kind of maybe 1s and 3s and 2s. You just have to remember to square the ones that have an exponent. That's the same idea. Let's try this one. This was a Menti question. People had qualitatively the right idea. Everyone correctly stated that as viewed from Saturn, the brightness of the sun is smaller than the brightness from Earth. But people were a little confused on whether it's a factor of 10 or a factor of 100. So again, the problem will tell you what formula is relevant. The brightness of the sun when viewed from Saturn 10 AU away is what factor brighter or dimmer compared to the brightness of the sun viewed from Earth 1 AU away. So given it's talking about brightnesses and there's distances, sounds like the brightness formula. So again, the relevant formula, B equals L, the luminosity of the sun, divided by 4 pi d squared. And again, we can make sure we know what each symbol means. Brightness, distance, and then luminosity. A measure of how much light is coming off the surface before it starts spreading out through space. So in this case, it's asking about what factor the brightness changes, which means we want to solve for brightness, but it already has done that. Great. We don't have to solve for anything. It's already in the right form. We want to know how brightness changes, so we should have B equals a bunch of other variables. I could remove constants, because again, they're not going to play a role. So then it looks like I have B equals L divided by D squared in this case. Then I have to ask myself, by what factor? It looks like there are two variables, L and D. By what factors are they changing? Well, D seems like I'm considering it from 1 AU and then considering it at 10 AU. So to me, that seems like a factor of 10. When I'm comparing Earth to Saturn, now you might say, why is it 10 and not 1/10? Well, it could be 1/10 if you're comparing Saturn to Earth, right? What's the brightness, right, of Saturn compared to Earth? Where here we're doing kind of Earth compared to Saturn. So Saturn is 10 times farther away in this case. And then for both cases, we're looking at the sun. So that suggests the luminosity in this case. The factor is 1, right? It's the same luminosity, the same star, the same amount of energy is coming off the surface of the sun in both cases. So then it looks like B is 1 divided by 10 squared. Can't forget the exponent. So then it is 1 over 100. So then, since we were comparing kind of Earth to Saturn, that says that the brightness of the sun at, again, we did Earth to Saturn, so at Saturn is 1/100th that at Earth. Or, said another way, B at Saturn is a factor of 100 smaller versus B at Earth. In this case then, right, it is dimmer because it's a smaller number, and it is smaller by what factor? Factor of 100. 100 times dimmer. Now again, if you were to do it the other way, maybe I'll just do it real quick. Since it's a video and goes as long as I want. If you wanted to do compare, or I guess, what is the brightness brightness at Earth compared to Saturn? So in a sense, we're starting at Saturn and then comparing that to what we get when we get at Earth. Now at Earth, is it a factor of 100 brighter than it is at Saturn? A factor of 10 brighter? What have you. Again, the luminosity is not changing, but then I would say the D is kind of 1/10 in that case. I go from 10 AU to 1 AU. That's a factor of 1/10. If you're confused with where the factors are coming from, or if I say 10 is going to 1, then what do I have to multiply 10 by in order to get 1/10, right? So it's a factor of 1/10. So then in this case, the brightness is 1 divided by 1/10 squared. You have a fraction of fractions. That's the same thing as 10 squared, which is the same thing as 100. So then the brightness at Earth is 100 times brighter versus B at Saturn. Now, if the ordering is confusing you, if you qualitatively know what the answer should be, then you can just calculate the number and then you know kind of how to word it. All right, if you know that when you go from Earth to Saturn, it should get dimmer, then if you calculate a number and you got 100, then what you probably did was, calculate Saturn to Earth, right? You would just reword yourself. But again, usually the wording will make it kind of clear what I want. Let me do two more that are worded a little differently, but still use the same approach, same idea. So here's one. You and your friend are measuring distances to stars. They observe one star with a parallax angle of 0.42356 arc seconds. Your star has a parallax angle that is 1/5 as large. The distance to your star, therefore, is 5 times larger, 1 divided by 1.42356 times larger, located at a shorter distance, particularly 42.356% the distance. Notice that's 0.42356 times 100. 5 times shorter the distance, 1/5 as large, or 5 divided by 0.42356 times larger. So we're measuring distances, and it seems like the problem is giving us parallax angles. That suggests that the relevant formula is probably the parallax formula, d equals 1 over p. Again, as long as p is in arc seconds, and as long as d is in units of parsecs. So the units, again, don't really matter at all when you're dealing with factors. So there are no we're asking about what's going on with distance. And it looks like I'm looking for a factor here. So then I should solve for the distance. It already is, great. Then the question is, by what factor? Well, first, can I get rid of any constants? There are no constants. And so then I have to identify on the right-hand side the factor by which all of those variables change. So there's only one variable on the right, which is p. And the factor in this case seems like your parallax angle is 1/5 as large. So I would say parallax is then going to be 1/5. Yours was 1/5 as large. Now again, there was enough information in the prompt that you could have actually calculated the exact parallax angle in this case. You could have then calculated the exact distance yours is at in parsecs and then compared that to theirs in their exact distance in parsecs, and maybe you would have noticed something. But here, notice we're going to avoid that completely. If I know the factors by which something changes, I'm gold. So then in that case, it looks like d, then I just plug in the factors. 1 divided by, and then I said the factor change is 1/5. Fraction of fractions, flip the bottom and multiply, so that just becomes 5. So again, not 5 parsecs, because we're thinking of factors. So then I would say the distance is 5 times larger than your friends. Right, the factor, your parallax angle is 1/5 as large. As a result, your distance is 5 times larger as a result. And again, notice we did not have to plug in anything messy. And if you actually wanted to calculate the exact values of their distances, you would notice that they're related by a factor of 5, of course. All right, last one. 2 stars, A and B, have the same brightness, but star B is twice as far away as star A. Therefore, the luminosity of star A is 4, 2, 1/2, 1/4, or the same as star B. First thing I would do, identify the relevant formula. Seems like I have mentions of brightnesses, right, the same brightness. Star B, though, is twice as far away. So I have something about brightnesses, I have something about distances, and then the prompts are asking about luminosity. To me, that suggests the brightness formula. So then I have B equals L over 4 pi d squared. Now, we are interested in luminosity. So my first step would be to solve for luminosity. So in that case, then I could write L is 4 pi d squared times B. I just multiply both sides by that 4 pi d squared in the denominator. In this case, now I have L, which is what I'm focused on, and then that's being written in terms of other variables, which I may know by what factor they're changing. So then I'm going to remove constants. So then I'm going to write L is d squared times b. Then I'm going to identify the factors on the right-hand side. So it looks like I have b and d. And if I go back up, it seems like the two stars have the same brightness, but then star B is twice as far away. So maybe the comparison I will do here is A to B. So when I go in terms of the brightness from A to B, I guess I should have used different letters, from capital A to capital B, star A to star B, the brightness does not change. It says it has the same brightness. So then this is just 1. But then in going from star A to star B, it says that star B is twice as far away. So then going from capital A to capital B, the distance doubles. It's a factor of 2. Then we just plug in the factors. So then the factor L changes is equal to, looks like it's d squared, so 2 squared times b, which is 1, and that looks like it's 4. So again, this 2 is kind of going from A to capital B. So then this 4 is going from A to capital B. So we could conclude, in this case, that if they have the same brightness but B is farther away, that the luminosity of B, I guess I should star B, is 4 times larger than star A. And again, as you become more comfortable with these sorts of expressions, you could think, does that make sense, right? It's always useful to ask yourself, do these things make any sense? I have 2 stars, and they both appear equally as bright in the sky, but I know that one is farther away. Well, think of 2 light bulbs. If I have 2 light bulbs that look the same to me from a distance, but I know that one of them is actually much farther away, that one that's much farther away must be more luminous, right? There's more light coming off of it to compensate. So, in this case, it makes sense that star B should be more luminous. So again, these sorts of examples, right? So we've seen this in the previous sort of material, where if you can identify the factors by which everything changes, you can then calculate the factor by which your variable of interest changes through these particular steps, which are also outlined on that course slide from lecture 29. So, hope that is helpful. And it's a video, you can watch it again. You can try to do them on your own before I write down the answer. This would be another thing that might be worth trying.